All right, here are solutions for perfect problem 5 from Math 213. The basic idea here is you have a cube in red, and then inside of it, it's dual, which is an octahedron. And what you're asked to do is to compute two things: the volume of the octahedron if the volume of the cube is 1, and the surface area of the octahedron if the surface area of the cube is 1. So let's take those one step at a time. If volume of cube is 1, and I guess technically we're talking about 1 unit cubed. Let's do some calculation. So if that's true, well, the formula for the volume of a cube is length times width times height. And so since the length, the width, and the height are all the same because it's a cube, and I multiply these three numbers, the same number by itself 3 times and get 1, those numbers must be 1. What I'm saying is each side of cube is 1, maybe just unit now. So I got 1 here, 1 here, 1 here. That'll be useful. I can think about this octahedron as 2 pyramids. Think of octahedron as 2 square base pyramids. So to figure out their volume, well, the volume of a pyramid is equal to 1/3 times the area of the base times the height. If the side length is 1, that means the distance from the bottom of this pyramid to the top is 1. And so that means the distance from the middle here to the top, that height, must be exactly 1/2. So I get that the volume is 1/3 times A times 1/2. And I got to figure out what A is. A is the area of the base. Well, the base in this case is a square. So let's figure out, find area of base. Well, let's see, maybe I need some color here. I could find the area of the base if I just knew the length of the side of the base. And so I can figure out the length of this line right here by creating a right triangle. So here's my best attempt at drawing a right triangle inside this picture. Not the easiest thing in the world to do. I have this right triangle, which maybe I could copy down here. Side of base equals S, maybe. Well, I know that this length, let's copy this triangle. This right triangle that I drew, the length of its legs are each half the distance of one of the side lengths of the cube. So I know the distance from here to here is 1, therefore the distance from here all the way over to here is 1, therefore the distance from here to here is 1/2. What I'm saying is this is 1/2, and similarly this is 1/2, and this is S. So I can use Pythagorean Theorem, say 1/2 squared plus 1/2 squared equals S squared. So this is 1/4 plus 1/4, that's equal to S squared. So 2/4, aka 1/2, is S squared. So S is equal to the square root of 1/2. So now that I know the side of the base is S, area of base is S squared. So I got A is equal to the square root of 1/2 squared, aka 1/2. So if the area is equal to 1/2, I can plug that into my formula up here and get 1/3 times 1/2 times 1/2. You multiply that out, you'll get 1/12. In other words, the volume of the octahedron, nope, that's not true. The volume of the pyramid is 1/12. But I have 2 pyramids, so this is the volume of the pyramid. The volume of the octahedron is 2 of these volumes of the pyramid. 2 times 1/12. This 1/12 went up here, aka 1/6. So if the volume of the cube is exactly 1, the volume of the inscribed octahedron here is 1/6. What about surface area? Well, let's see. If surface area of the octahedron is 1. Sorry, not the octahedron. The surface area of the cube is 1. Then I want to figure out the surface area of the octahedron. Well, if the surface area of the cube is 1, know that there's 6 faces on this cube. So each face has area 1/6. The 6 1/6 would make this 1. 1/6 unit squared if you want. Volume, this should have been units cubed, I guess. If each face has an area of 1/6, each side has length the square root of 1/6. Because each face is a square, so if this is the square root of 1/6 and this is the square root of 1/6, then when I multiply those together, I get 1/6, the area of each of the faces. So each side has length square root of 1/6. So I know that the length of one side of my cube is this number. But what I want to know is about the octahedron. I want to know about its surface area. Well, if I could figure out the length of one of the sides of the octahedron, I'd be in good shape. And the way I can figure that out is taking advantage of this same triangle. So I have this exact same triangle that I had before, except now, instead of this being 1/2 of 1, which was this 1/2, it's 1/2 of this number. So it's 1/2 of the square root of 1/6. And this is 1/2 of the square root of 1/6. And this is what I'm trying to figure out, S here. And you might be just plugging these into a calculator and getting decimal approximations at this point, but I'm not going to. I'm going to say 1/2 of the square root of 1/6 squared plus 1/2 of the square root of 1/6 squared is equal to S squared. When you square this thing, you get 1/4 times 1/6. 1/2 times 1/2 gives me 1/4. The square root of 1/6 squared gives me 1/6. Same thing happens over here. So let's see, I have 1/24 over here and 1/24 over here, so I have 2/24, aka 1/12. That's equal to S squared, and therefore S is equal to the square root of 1/12. So what that's saying is the side length of any of these sides has got to be exactly this length right here. So now I want to figure out the surface area. We'll recognize that the surface area here is just 8 equilateral triangles. So this is the side length of the octahedron. This was the side, each side of the cube has length square root of 1/6. So this is my side length of the octahedron. And so now I want to figure out how I can use that to figure out the surface area of the octahedron. Well, the octahedron is just made up of 8 equilateral triangles. Maybe I write that. Octahedron surface area is the sum of the surface area of 8 equilateral triangles. So I have these equilateral triangles here. And I know that their side lengths are the square root of 1/12. So the area of a triangle is 1/2 the base times the height. So 1/2 times the base in this case is the square root of 1/12. And the height, well, I'll have to figure that out. There's the height right there. I got a right triangle. So I can use Pythagorean Theorem. A would be half of this length. Right, this distance in green right here is half of the base. The base is the square root of 1/12. So half of that is 1/2 of the square root of 1/12. So that thing squared plus this length, or h squared, is equal to the hypotenuse, the square root of 1/12 squared. So when I square this side, I get 1/4 times 1/12 plus h squared. It's hard to read. Let's try that again. Is equal to 1/12. So this is, I don't know, 1/48, I guess, and this is 4/48. So I get that h squared is equal to 3/48, which conveniently enough for me reduces to 1/16. So all that to say, I'm short on room. I don't know, over here maybe? That's not even going to show up on the solutions. So h is equal to the square root of 1/16, aka 1/4. Hey, nice when numbers work out nicely. So I can plug that in down here and get that the area of the triangle is 1/2 times 1/4 is 1/8 times the square root of 1/12. So each of the triangles is 1/8 times the square root of 1/12. So 8 triangles. This is short on room. This isn't the area. The surface area of the octahedron is 8 times 1/8 times the square root of 1/12. Need to break this up somehow. Which is equal to the square root of 1/12. So the two numbers that I'm comparing are, let's see, up here I had 1/6. So let's see, which is greater, the volume of an octahedron inscribed inside a cube. So let's see, the volume of this octahedron, figured out that was 1/6 right here. Or the surface area of an octahedron, figured out down here that that was the square root of 1/12. So you're comparing the two of these. Let's see, the square root of 1/12 is the square root of 1 over the square root of 12, which is 1 over the square root of 12. The square root of 12 is less than 6, because 6 squared is 36, which is more than 12. So the denominator over here is smaller, which makes this thing bigger. The square root of 1/12 is greater than 1/6, so surface area is bigger. Exclamation point, because I'm happy to be done with that. Pretty challenging problem. I imagine that you didn't leave things in these exact notations, that you rounded off, and that's totally fine. You should come up with similar answers here. But I think these are the exact answers. So if you want to see how close your decimal approximations are to what the exact answers are, you can convert these into decimals and compare your answers. But this is getting pretty long, so I'm going to end this problem here.